Hey kids, you made it to the fifth and final video of the last unit of the year. This one is on light, and our essential question is, what is light and how do the wave properties impact what we see? So the question of what light is a lot more complicated than what sound is. We do know that light is a series of electric and magnetic fields moving through space. Of course, we haven't really defined what electric and magnetic fields are in this class. If you take more AP classes, you will learn about that a lot more. But suffice it to say that it's complicated. Light sometimes acts like waves, just like the picture shown, and other times it acts like a particle, like a little ball or something that is being thrown. So that kind of balance is known as the particle wave duality, and it's one of the things that makes light so special and interesting to physicists. In any case, you should know that most of light's observable properties can be explained from the same wave theory that we've been talking about in previous videos. So in order to observe or detect light, that light needs to be able to go into that hole in the middle of your eye called the pupil. Once that light passes into your eye, we have special receptor cells at the back of the eye called cones and rods, and they are the cells that help us determine the wave properties. For example, those cells can detect the frequency and the amplitude of light, and we'll talk about what we notice those properties as in a few minutes. But one thing that's a little bit different from sound is that we are actually able to also detect the location of the source of the light, which is really, really useful, of course, for humans to be able to tell where objects are based on looking at them. We'll talk in class about how the eyes can do that, but you should realize that those are all the functions of the cells inside your eye. The frequency of light is interpreted by human brains as different colors. So the colors of the rainbow, you may have heard the Roy G. Biv song, but red, orange, yellow, green, blue, indigo, and violet are kind of our way of describing different frequencies of light. Of course, there's no real cutoff between one color and the next. It's all kind of subjective, so what you might call orange, somebody else might call yellow. But in any case, we can typically detect a range of frequencies from 400 to 750 trillion hertz. So compare that to the sound frequencies that we can detect, which were fast. These are way faster. Those light waves are vibrating up and down trillions of times every second. And red is the lowest frequency, so vibrating the slowest. That's the color that we see. And the purple colors, the violet, are vibrating much faster. So those are at the high frequency end of the spectrum that we can see. The amplitude of light, of course, is the energy of the light, although there actually is a little bit of a twist that we'll talk about in a future day that Albert Einstein discovered. But in any case, in general, the more amplitude that a light wave has, the more energy it has, and it's caused by a stronger electric or magnetic field. In our brains, when we get a very high amplitude light wave, our brains interpret that as bright. So when you look at the sun, that's got a lot of amplitude. A laser has a lot of amplitude, but something like a candle would be light with low amplitude. The other light variables are not things that our eyes or brains can detect or interpret, but we do know a lot about the type of wave that light is, and the velocity of light, and the wavelength of light based on other scientific measurements. So it turns out that light is a transverse wave, so it's jiggling up and down, and we'll do some demonstrations in class that will prove that a little bit later on. But one thing that's really interesting about light propagation is that it doesn't require a medium. So every other wave that we've been dealing with has had to have a medium that it's moving through. Light can move through different media. We know it can go through water and glass and things like that, but light can actually travel through a vacuum, or the gap in space between air molecules as well. And we know this because if we look at the stars, we see their light. So light is the only kind of wave that can actually move through a vacuum, or the vacuum of space. Just like every other wave that we've dealt with, though, the speed of light depends on the medium that it's moving through. So if it's in that vacuum, which is basically the absence of a medium, that's actually when light moves the fastest. And the reason that it goes so fast there is because there's no atoms or molecules to run into. Those light waves are not slowed down by anything. That speed, the speed of light through a vacuum, is a really important speed in terms of physics. In fact, it's given its own variable. Instead of calling it v like the other velocities would be, we call it c, which is defined as the speed of light through a vacuum. It's otherwise known as nature's speed limit. It's the fastest speed anything can move anywhere. And the speed is actually 300 million meters per second. Interestingly, that's about the distance to the moon, 300 million meters. So if we turned a flashlight towards the moon, it would take about 1 second for that light from your flashlight to reach the moon. Whenever light travels through any other medium, whether it's water or glass or anything else, it slows down because the light waves are actually being absorbed every time they hit a little piece of that medium, and then they get re-emitted or spit back out again and continue moving. But that process, the absorption and re-emission, actually takes time. So light slows down when it moves through other materials. Wavelength is the last variable, and as I mentioned before, there is a specific range of frequencies that we can detect. That's known as visible light. There are, however, many other types of light that are just colors that we can't see. So we've got a whole range of other colors beyond visible light. The visible light wavelengths are on the order of a micrometer long, which is 10 to the negative 6th. So that's very, very small. And the wavelength is going to correspond with the color, just like the frequency does, because the wavelength depends on frequency. So, as summary, please revisit the essential question: what is light, and how do the wave properties of light impact what we see? Thanks for listening.